Hello, everyone, and welcome to the latest edition of the Lightning Interview Series. As always, we want to make these sessions interesting and interactive, so please do introduce yourself, tell us where you're joining from and what you do, and of course, please feel free to add any of your questions to our conversation. So today's interview, as you can tell by the title, is a very ambitious one. We are delighted to have today's guest, Professor Pedro Domingos from University of Washington, and we're going to be discussing the quest for the ultimate machine learning algorithm. However, before we get to that, I have a few quick words I want to say about upcoming events here at ODSC and AI Plus. First and foremost, we've got a lot of webinars coming up. Again, all these are free to join, so check those out when you have a chance. And we also take these videos, once this recording is over, you can find it on LinkedIn and YouTube, but also we have it on the AI Plus platform, which you can join for free. We have the likes of Emily Robinson's there. We just had an interview last week with Professor Michael Jordan, and a few months ago, Peter Beal. So lots of good interviews to check out there. And of course, our event of the year is coming up soon. We have ODSC Boston happening in May from the 9th to 11th. And we have training passes available there. And we also have free expo passes and other kinds of passes going on, as well as our usual scholarship passes. So go check that out. And some interesting new tracks there, including machine learning safety, ML ops, and we just did a small data engineering event, which is quite popular a couple of weeks ago. So we'll have a data engineering track as well, in addition to NLP, machine learning, deep learning, the usual suspects. And then do check out our AI Plus training platform. Lots of video, lots of content out there, free for you to use. And don't forget about our community service around if you're looking for your next role in computer science, AI, or machine learning. If you have a job available, you can post it on there for free. And if you're looking, go check it out. And we're using our NLP transformer learning models to match your resume pretty much to, I think right now we're doing all the AI machine learning jobs in the US and Europe. So a lot of these systems out there for careers are kind of use AI to filter you out. This is, I think of this as the reverse AI algorithm to help you better get ahead in your learning career. And that's it. So on to the main event. So I'm delighted to introduce today's guest, and none other than the incredibly accomplished and brilliant Pedro Domingos, Professor Emeritus of Computer Science and Engineering at the University of Washington. And as you may well know, the author of the book, The Master Algorithm. And in addition to that, he's co-authored over something like well over 200 technical publications in machine learning, data mining, and other areas. And well known for helping start the fields of statistical relational AI, data stream mining, one of my favorites, as well as adversarial learning, machine learning for information integration, and the influence maximization in social networks. He is also a fellow of the American Association for Advancement of Sciences and the Association of Advancement of Artificial Intelligence, and has received numerous awards over his career, including the NSF Career Award, Sloan Fellowship Award, Fulbright Scholarship, and IBM Faculty Award, and has several Best Paper Awards and many other distinctions, not least of which being the winner of two of the highest honors in data science and AI, the SIGKDD Innovation Award and the International Joint Conference on Artificial Intelligence, the John McCarthy Award. And I've actually had the pleasure of meeting Pedro on a number of occasions. I must say his modest manner conceals his brilliance, and he also has an incredible talent of being able to explain complex topics quite clearly. Pedro, welcome to the show.
Hi, thanks for having me.
So Pedro, I gotta admit that was a much longer introduction than I normally do, because again, completely enamored with your career in research. So I want to start with the first question. You've made so many contributions to the field of machine learning and data science and others, and you have an incredible track record as a researcher, as I've just kind of ran through. So would love you to fill our audience in on some of your research over your career.
Tall order. But let me touch on some of the main things. It's been amazing to be in machine learning these last 20, 30 years, because there's so much happening, right? And the amount happening and the impact that you have just keeps going up. So it's, you know, it was a good call to get a PhD in machine learning. Let's just put it that way. Of the things that I've done, probably the biggest and best known one is Markov logic networks, which is an approach to something that is very hot these days, which is combining symbolic and statistical AI. So Markov logic, as the name implies, is a combination of Markov networks, which basically includes all of the statistical models that we use, from the simplest ones like logistic regression to the most advanced ones like, you know, many types of deep network and whatnot. And on the other side, first order logic, which is really what all of you know, symbolic AI is based on. And the idea is to be able to do, you know, both of them with, you know, without doing one and then hacking the other. And I think you know, we've managed to make a lot of progress there. Another area that I've helped to start, actually, that's become which you alluded to briefly, is this you know, it's doing machine learning in social networks. You know, when I started doing it, there were no social networks. The largest data set that we have is like a couple hundred people. I can't say that without laughing now. And the idea was to model the social network as a graph and model the amount of influence that is going, you know, in the link between, say, you and me, how much do I influence you, and vice versa, and then use that for things like viral marketing. So viral marketing was a hot new idea when we did this research 20 years ago, and then you can predict who are the best people to market to get the biggest possible, you know, wave of conversion for the minimum budget, which, as you can imagine, is, you know, turned into a very popular idea from the smallest startups to the biggest companies. So that's another one. Another one that you know, was non-existent when we started doing it and now is huge is adversarial learning. Right. One thing that I you know, noticed is that, I mean, these days I think this is almost common sense, but there's still a lot of companies that, but in practice this is still largely not done. Is that when you deploy a model, the world changes in response to that model. People change their behavior. You know, many times in order to defeat your learner, like, say, you know, in the case of a spam filter, many times partly collaboratively, right? So the idea of adversarial learning is to model the fact that so the way we approach this was to say there's a game between the learner and some opponent that modifies the data, for example, to camouflage its activities if it can't be detected and whatnot. And of course, people have since discovered that deep networks are particularly vulnerable to this type of thing. And so there's a lot of work in that area. Another one is machine learning for data integration. Data integration, by some standards, is the biggest information technology problem on which, you know, according to Gartner, half of Fortune 500's budgets get spent. And our idea was to use machine learning to do some of that data integration. You know, to figure out what fields match in one database, match what fields in another, and which concepts in an ontology and records, you know, which records represent the same person, and to do that, you know, traditionally that was done using rules, you know, saying like, oh, you know, write a piece of SQL to convert this to that. But that, of course, is very brittle and doesn't scale. And our idea was to use machine learning for that. You can learn, you know, to map one thing to the other. And the advantage is that, contrary to the old approach, the more data you have, the better you do. And, you know, and there have been a whole bunch of things like that. I would say that one common theme in all of this, which I think, you know, may be of interest to people, is that I have always tried to be in touch with not just the information technology industry, but all industries and different fields of science, you know, talking to people and figuring out what are the problems that they have. Many times they don't even know that they have that problem because they take it as the world is like that. But you know, looking at it through machine learning eyes, you can see like, oh, you could apply machine learning here. And what I really like to do is notice that there's a common problem or sub-problem or abstraction of a problem that occurs across many different industries, many different companies, many different fields of science. And then I know that if I make some progress on that, it will have impact, because how could it not, right? So I think, you know, when you're deciding what to do, you know, as a research, as a startup, etc., that I think is a very useful approach. In a way, it makes it easy to have high impact, which otherwise might not be that easy.
Well, you've certainly had high impact, Pedro, to say the least. So let's get back to your 2015 book, The Master Algorithm, which I mentioned in the introduction. And I think that really helped popularize the field of machine learning. I remember when I read that book, you had a great phrase. You said, machine learning is the scientific method on steroids, right?
Yep.
Now, the central hypothesis of that book, at least that I took away from it, was that all knowledge, past, present, future, can be derived from data, which is definitely a key point, but by a single universal learning algorithm. So that was 7 years ago. You were working the book, I assume, 8 years ago.
Mm-hmm.
So what part of that book do you feel has stood up to the test of time?
That's a good question. Gratifyingly, I think the book, so I very consciously tried to write a book that would not be outdated in a few years. Because machine learning is moving very fast, was then and even more so now. And I wanted the book that would last. And so what I did for that was focus on the ideas that had been key for the last 50 years. And it's interesting that many of the key ideas actually have not changed in 50 years, hadn't, and still haven't. So the basic structure and ideas of the book are completely current, in particular the 5 major paradigms, what I call the 5 tribes of machine learning. They're still the same 5. None of it has disappeared and no new ones have appeared. Of course, I mentioned in the book that, every decade another one seems to be on top. And of course, at that point we were at the transition from kernel machines to deep learning. These days, deep learning dominates in the biggest possible way. But if you're going from history, probably, in another decade or whatever, another, paradigm will dominate. And maybe you already see the signs of that. So if I had to write the book again today or do a second edition, which my publisher has talked about, I would certainly add some things to the neural network chapter, because, for example, I didn't talk about transformers and attention and things like that there, and they are big enough that it's worth talking about. And again, the basic concept behind them is very simple, but a lot of people don't. There's a lot of confusion, like the rest of machine learning. So that would be worth doing. Clearly, the biggest part of the book that would need outdated is the last chapter on the future. So the first chapter is on the present, and the last chapter is on the future. And a lot of stuff that's in the future needs to be transferred to the present, right? I remember writing in one section, I said, like, what the tech companies are doing is a little short-sighted. We're going to wind up with a backlash and concerns, blah blah. This is coming. Boy, I had no idea.
You were spot on there, I must say.
I wasn't spot on. I was underestimating it, right? It's that has happened, but like in a much bigger way. So certainly the first and the last chapter are the ones that I think would need the most updating.
Well, let's get into it a little bit. I took the book off the shelf last night, albeit a little too late. Looking at the 5 tribes again. The symbolists, the connectionists, evolutionists, and Bayesians, and I think I'm forgetting the
analogizers.
Yeah, can you just for our audience briefly explain? Because again, I think we're going to share a link to the book. Go check it out. It's still a great read. Would be super interested in reading a follow-up edition for that for sure. Can you briefly explain the 5 tribes and then touch upon what you just mentioned? Who do you think, how they fared over the last 6 years, and who's pulling ahead, so to speak?
Right. So the symbolists are the tribe that for many decades dominated AI. And they're the ones that I start with. And the basic idea behind symbolic AI, and John McCarthy was really the main guy who started that, is that we're going to do AI by emulating the way logicians think, mathematicians. He was a mathematician. And so naturally, we're going to do AI. Well, let's base it on logic, because logic, in a way, is the formalism of thought. And this idea that you've alluded to of automating the scientific method, that is the tribe that's probably closest to that, is that we're going to build an artificial scientist. We're going to create a system that works like a scientist and therefore can discover things like scientists do. So that's the symbolist. And traditionally, their big rivals have been the connectionists, who are the people who say, nah, that's you're not going to get that way, because what scientists do on logic and conscious thought and reasoning are just the tip of the iceberg. You got to look at the whole iceberg and the part that's underwater, and that's your brain and how your brain works, right? Symbolists say, like, we should, the symbolist idea is very natural in computer science, is we should ignore the implementation and just think at an abstract level, regardless of whether you're doing it with neurons or transistors. Very, plausible, very productive, but the connectionist from joined today is like, no, you can't really ignore that, number one. And number two, you get a lot of good ideas by reverse engineering the competition, right? We're trying to, our competitor is the human brain. We're far behind. So what do? You open up the box and you see what's inside. So the connectionist idea is like, let's look at neurons and how they work and how they're connected, and try to build learning algorithms based on that. And of course, that idea has been spectacularly successful. It has also, like all of these, evolved far from its origins. A lot of deep learning these days is not particularly tied to the brain, but that's where it comes from. And certainly many of the key ideas, like, Conrad's, for example, etc., just come from there. Then there are the Bayesians. Sorry, before I go into the Bayesians, let's do this in the best order. So connectionism is basically doing machine learning and AI based on biology, right? But there's another way to do it based on biology, is to be inspired by evolution. And that's what the evolutionaries do. They say, like, well, sure, that's all very nice, but all that your brain does is fine-tune the connections of an architecture that was already there, right? So you're only doing half the job. Who does the rest of the job, or most of the job, maybe? It's evolution, right? The greatest learning algorithm on Earth is the one that Darwin discovered. So that's what we should be trying to emulate. We should evolve, again, a very natural idea that goes back to the 50s. Like all of these, they were all born in the 50s, maybe except some of the, as machine learning approaches, at least they were all born in the 50s. So the idea is like, let's implement evolution on a computer, and instead of evolving animals and plants, we're going to evolve programs and circuits and robots and whatnot. Now, counter to that, there's the view that, like, now taking inspiration from biology is just it's a bad idea, because biology is hacky, evolution is random, your brain is full of crap. Who needs that, right? You're making your life harder. What you should do is figure out how to do machine learning from first principles. And the symbolists are a little bit of that, but the champions of this are the Bayesians, right? The Bayesians, of course, have their origins in Bayesian statistics, and they are the hardest core of the tribes. To a Bayesian, if what you do is not Bayesian, you're just doing it wrong, buddy. Sorry. Like, you got to learn to do it right. And they also are very imperialistic, in the sense that, like, there's a Bayesian version of neural networks, or many these days, a Bayesian version of symbolic learning, a Bayesian version of everything. And whatever you come up with tomorrow, I'm sure there's a Bayesian version of that. The Bayesian idea is, again, it comes from statistics, and statistics has historically been dominated by frequentism, where probabilities are just counts, essentially. The Bayesian idea is that a probability is a subjective thing in your mind. You start with your prior probabilities about what's likely and what isn't before you see the data. And then as you see data, your probabilities evolve into what is called the posterior probability. And it's all about computing probabilities and updating them with data. And then, of course, you get this incredibly heavy computational problem, and a lot of the work is on making it more efficient. So that's the Bayesian approach. And then finally, there's the analogizers, which are actually the least known, least loved, and least cohesive of the tribes. But ironically, when you talk to lay people, easily the one that they find the most intuitive, right? They don't know about connectionism or logic or symbolism, or let alone Bayesian statistics. But the idea of reasoning by analogy is very natural to most people, because indeed, psychology shows that's what we do. And the idea there is, when I have a problem to solve, I find a similar problem or set of problems in my past experience, and I transfer the solution. I notice the similarities, I combine things. Again, there's a bunch of different ways to do that. And the best known, but also one of the simplest ways of doing this, is kernel machines, or even going further back, nearest neighbor. So nearest neighbor is a remarkably powerful learning algorithm. It was the first one. You could even say that machine learning began with the nearest neighbor algorithm, because it was the first algorithm that had this property that if you give it more data, it will get better until it knows the function almost perfectly. Okay, so nearest neighbor is an analogy-based method. Kernel machines, right? The kernel is your similarity function. But then there's much fancier things coming from psychology, like structure mapping, where you map the structure of one problem to another. And indeed, this is what people seem to, like the guy who coined the term analogize is Douglas Hofstadter, the author of Gödel Escherbach, which a lot of people, in the computing world know. I know many people got into AI because of that. His most recent book is about how everything is analogy. From the most banal, subconscious daily things to the greatest leaps of genius from, Einstein and whatnot. So there you go. Those are the 5 tribes.
Pedro, thank you for such an illuminating answer. And I know you're probably tired of answering this question, but which tribes, should I say, are you finding yourself in these days?
So a lot of my work, and part of why I wrote the book as I did, so my belief, and this was my belief from day one, is that none of these tribes has the whole answer. Each one of them does something very well, but they solve one problem. And to really get AI, we need to solve all 5 of those problems. For example, connectionists have backprop to solve the credit assignment problem, a really important one. But the symbolists know how to learn composable knowledge, which is also very important, and neural networks still can't do, etc. So you got to unify them and start. So my PhD was unifying symbolic and analogical AI. A lot of my work, as I alluded to before, was combining symbolic and probabilistic / Bayesian AI. More recently, I've done I did work combining Bayesian and neural. And these days, the main thing that I'm working on, or one of the few main things I should say, is combining symbolic with neural. Like there's this whole field of neurosymbolic AI, which when I first got interested in it 25 years ago, nobody was interested in it, and these days it's a really huge thing.
Yeah, fascinating. And but just like you're saying with the 5 tribes, because to anyone's ears, whether you're a practitioner in machine learning or a novice, the master algorithm sounds like the holy grail of machine learning research, and where we can learn anything from data. So how close do you think we are?
We are definitely closer than when I wrote the book. Right? I mean, it's been quite amazing and gratifying to observe. So first of all, there are these companies like DeepMind whose explicit goal is to come up with a master algorithm, right? They want to come up with a learning algorithm that will be able to do everything, from science to playing games to you name it. And then there's also these efforts from companies like Google prominently, but also Meta and OpenAI and DeepMind and whatnot, to have a learning system that will learn from all different kinds of data. Like Gato, for example, from DeepMind is a good example of this, right? It's a transformer, a very popular architecture these days, but it doesn't just learn from text or learn to say things. It learns from text and images and robot actions, and then it learns what to do. So if that were to succeed, it would be the master algorithm. Right? And again, the other companies have similar efforts. Now, I don't think those things are the master algorithm yet because of a number of limitations and issues that we can touch on. But clearly, finding the master algorithm has gone from being sort of like a crazy idea that a few people had to what a lot of these companies with a lot of resources are gunning for. And they're gunning for it for very good reasons, because whoever gets that first will have a very, very bright future.
Yeah, and we've seen that with Microsoft's announced $10 billion investment in OpenAI, and that begs the question: where do you think it's going to emerge from then? Is it going to be existing AI such as predictive coding, or OpenAI they specialize in reinforcement learning, or is it from ideas and research that have yet to come?
Yes, so that is a great question. And I think that, first of all, we do need to combine those 5 major paradigms in one way or another. How you do this, there's a lot of different approaches. There are a lot of combinations 2 by 2, but at this point we have 3 and 4 and 5. And I think at this point we have a good idea of how to combine all 5 at some level. Of course, at some level means, for example, scaling up and whatnot are very big issues that need to be solved. But my intuition, and I can't prove this, is that at the end of the day, that's not going to be enough. So at one end of the spectrum, there are the optimists or the hardest core members of each tribe who really think that their paradigm is all you need. So there are people, in deep learning today who say, like, backprop, you can do everything with backprop, right? I have this ongoing discussion with Jan LeCun where he says, like, gradient descent is the only thing you need for learning. There's nothing but gradient descent back. So that's his belief, right? Most people are not that optimistic that a single, usually in any one decade, as I mentioned, one paradigm is dominating, and the members of that paradigm are very gung-ho and saying like, we're gonna run this all the way to human level AI, and then it doesn't happen. At some point, maybe it will. Maybe that point is this point, but probably not. So I think we need to combine all of them. But then I think even after we have, we will find, unlike other fields, like for example physics, where we know what the main forces are, and once we unify them all, that's your full account of the world, right? The standard model captures 3, and then you add gravity, and you're done. I think in AI we will not be done. My feeling is that there are really important ideas that we need to have that master algorithm that have not been discovered yet. And in fact, another big piece of my research these days is working on precisely that. And now you can ask yourself, so where are those ideas going to come from? And and I have some thoughts on that. In fact, they could come from a whole slew of different places, but I also think some look more promising than others. It's good to bear in mind that these 5 paradigms that continue to dominate AI, they all, this part of what makes machine learning fun is like they all took their main idea or ideas, but often there's one main idea from some pre-existing field. Right, from philosophy and logic in the case of the symbolists, from neuroscience in the case of the connectionists, from evolution, from Bayesian statistics, from psychology. But usually when a field is mature, it's because it has developed its own ideas, not just porting over ideas from other fields. And I think that part is actually yet to happen in machine learning. So the next 10 years are going to be even more exciting than the previous 10.
Yeah, and you bring up some interesting points there. Would love to go into a little more, but bringing the conversation back up a little bit. So right now, as you're touching upon it, what are some of the biggest limitations of machine learning today that are getting in the way of this?
No, exactly. And in fact, these 2 questions are closely related, because if there weren't those big limitations, then we'd be almost there. But those big limitations are there. And interestingly, to my mind, and not just my mind, the biggest limitation is actually the same for all of these paradigms. You could say it's the great unsolved problem of machine learning. And this is the fact that learning algorithms do not generalize nearly as far as you and I do. They generalize only a small distance from the data. And as you move further away from the data, things crash, which is, for example, what makes them so vulnerable to adversarial attacks. And we can paper, in fact, what we have been doing very successfully for the last 20 years, but particularly the last 10, is we paper over that by having ever more data. Right? It's like a Swiss cheese where we're making more and more holes. Everywhere there's a data point, there's a hole, but we're very far from having eaten the whole cheese. The cheese is not 3-dimensional, it's a million-dimensional, and it's still 99.99999% cheese. So we need to figure out ways to generalize further. Right? And there's always this accusation, which in a way is an oversimplification, but has some truth, that like, oh, all this learning, all this deep learning, all this machine learning is just interpolation. Right? It's not just interpolation, but it is the fact that if you think about it from that point of view, see where interpolation in a very large space, right, is missing something, right? You're not going to get the kind of intelligence that humans have just by doing that. And the thing is, we do know that it's possible because you and I and any 2-year-old kid do that, right? You show a 2-year-old kid a picture of a horse, and they know horses for the rest of their life from then on, from one example, right? So there are a lot of things to try to do this, many of which I've worked on, things like, transfer learning, one-shot learning, domain adaptation, there's, meta learning. There's a whole bunch of different things to try to deal with this. I think they're all good. I think, I don't think any of those is going to get us all the way there. I have some ideas on how to do it. In particular, I think there's a new paradigm that is starting to grow. Again, interesting, because like when we started doing it, some years ago, nobody was doing it essentially, and these days it's actually a large and growing field, which is symmetry-based learning, or sometimes called, or one aspect of that is geometric deep learning, which is bringing, interestingly, ideas from yet another field, which is physics and mathematics, and the idea of symmetry groups, and using symmetry groups to base symmetries are invariances of objects, right? So if you think about it as invariances, there's a very well-developed theory of invariances that is very important, very central in mathematics and physics. And the simplest example of that in machine learning is convnets. Translation invariance is what a convnet is. How a convnet differs from a regular multilayer perceptron is that it encodes translation invariance. But there are many, many more invariances, first to encode and second and most important, to discover. Right? I think your brain is an amazing invariance discovery machine, and that it knows how to compose them and reason with them. And the key thing is that one of these invariances is a transformation, like, for example, a change in pose, can be very simple, but then they can be composed. So I can discover 100 of these symmetries from 100 different pieces of data, each of them easy to discover. But then if I compose all of them, I can wind up with something that is dramatically different from the training data. For example, pictures of cats. I can recognize a cat that looks very, very different in all these respects from the ones that I trained on, but I'm still able to reliably recognize it. So this is one approach that I'm pursuing. Some people have jokingly called it the sixth paradigm. So maybe in my next book, in the Dan Brown vein, could be called the sixth paradigm.
I love it. I would say go with that. Is there a poll on this StreamYard thing we can use? That'd be kind of handy. Do some real time polling there. And actually, I did watch a couple of months ago or last month a lecture of yours on YouTube on symmetry-based learning, which is the first I've heard of it, Pedro. So again, very illuminating. That's on YouTube. Just search Pedro on YouTube. You'll see lots of good videos there anyway, and check that out. And yeah, just an interesting point about large language models. So Andrew Ning started talking, I think, mid last year about data-centric AI. And one thing I've kind of found over my career as a practitioner, open data science and all that stuff, being very enamored with open data. The amount of open data out there is not as much as we think. Most data is proprietary. It's closed data or it's licensed data. And we've talked a lot about models. But are you concerned? Like, I think someone made a comment about ChatGPT. I was reading lots of stuff about it, but there's a limit to how far these large language models can go, because they're soaking up all this data. ChatGPT, based on GPT-3, can what is it, up to 2021? Yeah, and we're generating more data. But any concerns about that, and thoughts on the data-centric nature of this to get us to the ultimate algorithm, so to speak?
Well, obviously, yes. So data is very powerful. Because it's very powerful, data can be a key competitive advantage, or even sometimes the key competitive advantage. So companies aren't all going to share their data, because that would be suicidal. At the same time, the amount of data that is public will continue to grow. And at the same time, it is true that the likes of ChatGPT are running out of data to train on, right? We need to get people to talk more and write more and have more children and colonize other planets, so we have more data to train ChatGPT on. Of course, I'm joking. This, of course, gets back to the earlier point that we can't keep doing this forever, right? At some, in a way, it's the easy thing to do, and OpenAI has done it very well, is to just scale up and get all the juice that we can out of that. But something that I realized very on in my research, which initially was very focused on scaling up, is that you hit it. At some point you hit a wall. You're using all the data that you can, all the data that you have, and you're still not as smart as you'd like to be. So we do need to find better ways to. I mean, like, we need to get them more leverage out of the data that we have, right? These days, there's even this notion that, like, machine learning is all about large amounts of data. You can know a lot of very good machine learning with 200 examples. It all depends on what the application is. And I think what we're going to see, going forward, we're already starting to see that, is that what is the role of these large language models? They kind of like a new type of platform, right? A platform is a technology that you can then build other things on and combine them and go on to the next level. And what we have now is that, like, you have this, they're being made available by, Microsoft and Google and whatnot. And you can use your large language model as one source of knowledge, features, etc., for what you want to do. But what you want to do is going to require your own machine learning on your own data. So at the end of the day, you're going to have a model that combines at 2 levels or even more levels, public data with private or very classified data. And in the old days, you just used your own. You learn, like, I want to do credit scoring. I had some data for credit scoring. Period. These days, in addition, I can use the likes of ChatGPT. That alone probably won't make the best credit score model that is, but it's a very useful thing to then I mean, ideally, what we'd have is an AI that has common sense knowledge and et cetera, and then we will build on that. That's what we're aiming for, right? But in the meantime, something like a large language model is an approximation to that. So you use that as a platform, but then you have to do your own learning with your own private data on top of that for the application that you really care about.
By the way, for our audience, please add your own questions to the conversation. Some great comments there, I see, in the comment section. Yeah, and one other point about I loved about your book that has been very much an evergreen nature to it. You mentioned that you want to empower people to understand ML, but also to own their own data. And we just had Michael Jordan on the show last week, actually, and we're talking about agency and in relation to agents. Do you think progress has been made there since 2015, or because when I'm using AI, mostly I'm using a model that's not trained in my data whatsoever, or it's using reinforcement learning tracking data. Do you think we've made progress there, or not so much? Like, when are we as individuals going to get agency around our own private data?
That is a great question, and the answer is we've made progress. Unfortunately, we are further behind than we were then, because things have moved even faster than the progress that we made, right? So, but to start with the progress, I remember when I was writing the book, thinking, like, if at least machine learning becomes, not a household word, but a word that people know about and is part of the discourse, this book will have been successful. We're there now, right? When I wrote the book, machine learning was not a term that would appear in the media, for example, or if it appeared, it would be with like quotes. There's this machine learning technology, and now not everybody knows about machine learning, and that's good, right? And people are aware. Again, back then they weren't, that like all these computer systems that you're interacting with, from a search engine to a recommender system to Facebook and Twitter and whatnot, they're all using machine learning, and you need to understand what they're doing so that you can use it to your purposes. And not people are aware of that, or at least many people are, and that's good. So we've made progress there. However, again, and I say this in the introduction to the book, I'm not trying to give people like a detailed technical understanding of machine learning, but you need to, because you don't need that to use machine learning or to manage things that include machine learning and whatnot, but you need to have a good conceptual model of what machine learning does. And the conceptual model that people have today is still full of misconceptions and oversimplified, and I wish people were farther along in that, because again, these days it's even more important than it was then, right? AI is coming for your jobs, so they say, or like, I think more realistically, you want to use it, you want to figure out how to use it, you need to understand what it does and how it works and what its limitations are. ChatGPT is a great example, right? There's both a lot of overhype and a lot of people who think it's just hype that isn't. So, and also machine learning has evolved very fast. So in some ways, it's hard, it's harder to understand what the machine learning algorithms are doing now than it was then. It's one thing to understand naive Bayes or nearest neighbor. It's another thing to understand the transformer with, contextual embeddings and et cetera, et cetera. So I think we've definitely made progress. There's more progress to be made. One aspect of this, which again, we've made progress, but there's more to be made, is that, I advocated in the book and continue to, both, in public and with the relevant companies, that they should be more open about the AI that they're using, right? Trying to keep it all under the hood in some ways is the easiest thing to do, but it's dangerous, as I said back then, and we've touched on, because then at some point people are like, well, what's going on here? You're trying to manipulate me, et cetera, et cetera. So people should be able, I as a user of Amazon should have more control over the recommender system than just, it mined my data and says that, hey, are you interested in watches? But I just bought one, so I don't need a watch at this point. Or, a whole bunch of things like that. So, people are more aware of what's going on. I think, there's a bunch of heuristics in the book for, like, when you're interacting with the system, for example, realize that you're both accomplishing your immediate goal and teaching that system about you for the future, right? Very important to think at that level. And I think people are kind of aware of this at this point, but not really yet of, like, in the ways that they could or should change their behavior. and the companies are really not facilitating as much as they could and should. So, I mean, I think we're getting there. We're making progress in that direction, but we could, the progress could be faster, and there's a ways to go still.
Excellent. Just taking an audience question there, Pedro, if you can see that from Chuck. Very interesting topic, semi-supervised learning. Do you see that question there?
Yeah. Yes, so semi-supervised learning is I think a priori a great idea, right? Because it combines the best of both worlds. The advantage of unsupervised data is that there's a lot more of it. The advantage of supervised data is that the one that really teaches you how to do your task. And again, the analogy with people is most of the learning that children do is not supervised by their parents or teachers. So we want to do that as well. But then at the end of the day, you do need to get supervised, or at least it's good to get supervised to learn some things well and faster. And it works, right? Semi-supervised learning to a large extent works, and we have a good understanding at this point of, for example, how to combine the two and when the combination might work and might not work. At this, you could say that in depending on how you. Depending on what you think semi-supervised learning is, you could say that it's widespread today. Now, for example, you mentioned self-supervised learning, right? One way to think about self-supervised learning is it really is just semi-supervised learning, right? Let's take a concrete example, like large language models, right? A language model is a type of unsupervised learning, right? You're just learning, the probability distribution over sentences that people write or speak, right? But now the whole trick, and I think what justifies this term self-supervised learning, is that and it is a very good trick to use, is that you convert the semi-supervised learning problem, the unsupervised learning problem, into a supervised one. So, for example, in large language models, what you do is you predict the next words from the previous ones. And if you do this from the beginning of the text to the end, you've just predicted a whole, the whole text, right? So you've generated it, right? So now it's a generative model, right? Another way to look at this is in terms of generative models and discriminative ones. Generative for the unsupervised, discriminative for the supervised. So anytime that you can do that is a huge win, right? So whether you call it semi-supervised or self-supervised, it's definitely, a good idea. And one of the key ideas powering, the advance of machine learning today.
Yeah, and I think just a follow-up question there from Chuck. What do you think of probabilistic generative models? Will they come back like neural networks? I guess that's that's Kahn's Markov models. Yeah, I'll let you answer the question, Pedro.
Yeah, so this gets back to those tribes, right? So there's the tribe that does probabilistic generative. So again, if you talk to a typical Bayesian, discriminative learning is a wrong thing to do, right? You need to the scientifically correct thing to do is to learn a model in the form of a probability distribution of how the world generates the data, and then based on that, you can using the right loss function, the discriminative learning, or whatever else you want, right? Now, it's important to realize that a lot of the deep network architectures are probabilistic generative models. So deep Boltzmann machines, deep belief networks, et cetera, these are literally, they are a type of generative model, right? The probability distributions, so you could say that, for example, what Geoff Hinton does, or has done for the most part in his career, has been generative modeling, right? And, he famously says, or at least he says privately, that he doesn't like discriminative learning, he just does it because he needs to publish, to publish the papers. So, and maybe even more telling, many people in the audience are probably familiar with the deep learning textbook by Ian Goodfellow et al. And that textbook has two main sections, right? One section is machine learning, deep learning as we do it, which is backprop and multi-layer perceptrons and whatnot. And the other one, the last third of the book is deep learning as we'd like to do it, and those are probabilistic generative models, which again become difficult because the cost of computing these probabilities is so high, and then you get into that whole neck of the woods. But you could say that in a way, probabilistic generative models have never gone away. A lot of what people call generative models these days, starting with GANs, but now with things like LLMs and whatnot, the generative models in a weaker sense of generative. It generates images or text or whatever, but they're not really probabilistic. But maybe the core question here at the end of the day, and there are very different opinions on this, is like, at the end of the day, are you better, let me focus on the probabilistic, right? Should your generative models or should your models be explicitly probabilistic or not? One answer is absolutely, that's the Bayesian answer, because anything else is wrong. Another answer is like, well, no, because that incurs a very large computational and data cost and whatnot. And we can, achieve the same effect while making these heuristic compromises. And certainly right now, the latter approach is winning big time, like, 100 to 1. And maybe that's what will happen, all the way to the goal line, or maybe not. My mind is actually open on that question. I think it could go either way.
Well, let's have you back in 5 years, Pedro, and we'll figure this out. But let's talk about something everyone's talking about, but in a kind of a slightly different context, around the ethics of AI. So OpenAI back in 2019, they didn't want to release, it seems like a lifetime ago now, they didn't want to release GPT-2, that was early 2019, because they were worried about it's going to generate spam, people are going to use it for malicious use, like writing fake news articles. But then they released it by the end of 2019 anyway. And then they came up with an even more powerful model, which was GPT-3, which with some very nice engineering became ChatGPT. And as we've all been following this story, the general reaction has, as I mentioned earlier, a lot of ink spilled. And the reaction has ranged from hype to hysteria and everything in between. And lots of stuff. We could spend a whole show just talking about that. But also, even prior to ChatGPT, there was a lot said about AI regulation. So what does ChatGPT say about where we are with the ethics of AI in terms of tools we use, who's responsible? So do you think this is going to be a bit of a turning point of in the ethics of AI, or just one more pit stop in the journey?
I don't think it will be a turning point, but it's going to make those issues even more salient. And it is important to think about, AI ethics, or what are the social and economic and political implications of AI, right? Any technology that becomes sufficiently important and powerful is going to have everybody trying to do their thing with it, legitimate or illegitimate, legal or criminal, left-wing or right-wing, democratic or authoritarian, et cetera, et cetera. And AI is an unusually powerful technology. So, this is unavoidable, right? Again, it's part of why everybody needs to understand a little bit of AI, is because there are a lot of decisions to be made about it, and you want to be part of them. And if you don't understand AI, you really, you're just going to, you're at the mercy of the ones that do. Now, when OpenAI said, as you very well put it, like what seems like ages ago, like, oh, we're not going to release this because of the ethical implications, I think the reaction of most people in the field was like, oh, come on, right? It's like, when you have a technology that is this, it's like saying like, I'm Isaac Newton, I just invented calculus, but I'm not going to tell anybody about it because of the ethical implications. It's like, you're thinking at the wrong level, right? Anything that's that general, it should be released. And then we need to figure out how to do good things with it and stop the bad ones. But it's not like, and of course, they've now completely given up on that and gone the exact opposite directions. Like, anybody can use ChatGPT, and it's the biggest success they've ever had, right? So I think they figured out that wasn't kind of like getting them anywhere. But now, of course, the substantive question is, what do we do with these technologies, right? And I think, again, part of what's a little frustrating, so it's good that people are now aware of the issues that AI raises. What is frustrating is that people are very focused on the wrong issues, which takes all the oxygen up, and then the real ones, which are very serious, actually don't get the attention they deserve. So, for example, right, first and foremost, there's the Skynet scenario, right? A lot of people worry about like, oh, the robots, they're going to take over and kill all of us. And then how do we stop that? And the thing is, first of all, that is nowhere near, at least if you ask most experts, including myself. And second of all, there are many, many ways where that's much less likely than you think, and that we can stop it, and so on and so forth. So it's not, it's like Andrew Ng has a famous line, which I agree with, which is, worrying about that is like worrying about overpopulation on Mars, right? And you're like, let's get to Mars first, right? And build a base there. And maybe at some point overpopulation will be a problem, but not saying like, no, let's not go to Mars because we might overpopulate. It's like, oh, come on, right? So this is one thing. The other thing, which you also see a lot of these days, is people of different political persuasions. And, this is very natural and human, is like they project their preoccupations onto AI. So if you're a libertarian, AI is big brother. And, there's a danger of AI being big brother, don't get me wrong. And if you're a liberal, AI is like a discrimination engine. It's biased left and right. And, again, those are real problems, but AI can be the biggest engine against bias that you ever saw if you use it properly. In the meantime, and the common theme to all of these, the Skynet alarmists, the big brother, the cesspool of bias, is like, you gotta chain AI and limit up what it can do, and because it's dangerous. And the thing is that, like, if people only take one thing away from this interview, I hope they remember this. The danger is not AI that's too smart. The danger is AI that's too stupid. Right? The biggest problem of AI today is none of these, is that AI is already making very consequential decisions, like, who gets interviewed for this job, who gets credit, whatnot. And they make mistakes, not because they're biased or evil or whatnot, but because they're stupid. So stupidity in AI is the biggest danger, right? People are afraid that computers will get too smart and take over the world. But the problem is that they're too stupid and they've already taken over the world.
That's such a simple but astute observation at the same time.
I mean, again, people have this image of AI as like, from the movies as a very powerful thing, but and one day it will be, it's going to get there step by step. But the problem right now is that it's not powerful enough. So the best way to make AI safer across the board is to make it more intelligent, right? So people need to focus on what the real problems are as opposed to the, imaginary ones. The other one, of course, is that, so the two big problems with AI are, number one, it's too stupid. And number two is, like, it can be used for nefarious purposes. So criminals can use AI, authoritarians can use AI to repress people, as they do in China these days. And that is indeed a very serious problem that we need to worry about. But I think, again, in a country like China, you need to worry about the use of AI by the government, right? In America, American people, for example, are very different in this. In Europe, people trust the government more. I'm not, Europe has made a lot of laws restricting the use of AI by companies and so on and so forth. And they're well-intentioned, but often they create a lot of, they do more harm than good because they restrict things that shouldn't be restricted and vice versa. And the thing is, I'm much more afraid of AI in the hands of an authoritarian government, because the government can put me in jail or kill me, or in the hands of a company, because the best the company can do is try to manipulate me into buying something. And the thing is that, like, is very limited. Like, like, how much does Google, like Google, right? Oh, Google is Skynet. They manipulate, like, Google shows you ads, right? How many of those ads have you actually clicked on, right? So again, people have this vastly exaggerated notion of what the power is that these companies have to manipulate with AI. So, we have to be realistic and focus on the big problems, not the big current problems, not the ones that we've projected onto AI, are the ones that, are very far in the future, if they're there at all.
Yes, no, very, very well said, very well put. And yeah, there's been so much debate about it, and illuminating debate. And I think one I was kind of following a little bit was, a few researchers have come out and said, look, there are some startups and research labs out there doing even more advanced stuff than what ChatGPT is, and that's added even more angst. And because at the end of the day, it's it's been, as you put, like, we're just going through the research there a while ago. It's transformer architecture. It's semi self-supervised learning, reinforcement learning for sure. But do you think, because you brought it up in your book as well, to make sure everyone benefits from AI, do you think, like, projects like ChatGPT are going to democratize AI, to use a favorite phrase of everyone out there, much like Alexa and Google kind of brought AI into the home, or do you think it's just, as Jan LeCun, I think, put it, it's just a well-engineered model?
Well, I think
transformational.
Well, I think both of those things are true, right? And it's very important to be able to keep those two apparently contradictory ideas in your head at the same time. So I think AI is becoming democratized, and ChatGPT and things like it are another step in the democratization of AI, and that's really good. So democratizing AI is things like something that this was always one of the goals of my research, or one of the things that motivated me, and it's beautiful to see it starting to happen, is everybody should be able to program. You shouldn't need to learn, Python or Java or C++ in order to get the computer to do what you want it to do, right? We who know how to program have an enormous amount of power, but everybody should have that. Everybody should say like, hey computer, right? Or hey Google or Siri or whatever, I want a system that does this. Or, I don't like how this app works, change it to do that in natural language and have that happen. And we are visibly closer to that now than we were, 2 years or 5 or 10 years ago, right? Still farther than a lot of people think. Again, the hype has gotten ahead of reality, as is often the case, particularly in AI. But we are making progress in that direction. This is a great thing, right? Democratizing AI, first of all, it's good for each one of us, because now I can, use AI. You should have sort of like AI as like your continuous everyday helper in everything that you want to do. And that is the goal of Siri and Cortana and Alexa and all of those things, right? It's just that as the technology progresses, we are increasingly able to do that well. Again, better now than 2 years ago, but still not, not nearly to the degree that we'd like to have. So that in itself is good, but also once everybody can program, think of how much that speeds up progress, right? We don't have the bottleneck of the people who know AI or software engineering anymore, right? So, I tell the computer to create this app for me, and then I share it with you because you're my friend, and then before we know it, if there's a billion people who benefit from it, they're using it, right? So this is all great. Now, how you democratize AI, there's a whole lot of things to be said there. Now, to Jan's point, it is true that ChatGPT is just a well-engineered system, right? So a lot of the old timers, like him and me, right, like the natural tendency, and I've heard this from many different people, is to say like, oh, come on, what is all this fuss about, right? ChatGPT is a bunch of ideas that predated it, just scaled up. The only thing they've done was scale it up some more, right? And my answer to that is, well, scaling up is a good thing to do, right? You shouldn't, people should have learned this by now in machine learning, is that don't look down on scaling up, right? Human brains are just monkey brains scaled up, right? And look at all the things we did that chimps don't. So once you have the right thing, scaling it up, is a big deal. My experience, however, is that we don't have the right thing yet, such that just scaling it up will get us there. But in the interim, scaling up what we have, like OpenAI has been doing, is a good thing. And scaling up is not trivial, right? Anybody who has worked on scaling up machine learning knows this. It's not like you push a button and now you can do it with, at 1,000 times the scale. There are interesting and difficult technical problems to be solved at every step of the way. And that's actually one of the areas where we've seen the most, progress in the last few years. Not just, OpenAI, but Google, things like, TPUs. And there's a whole set of things there. So scaling up itself is not trivial. But the other thing to realize is that when I look at ChatGPT, I don't just think of what OpenAI has done. I think of all the things that went into it. Neural networks and backprop and Atom and layer normalization and GPUs and language models and contextual embeddings and attention and transformers. So GPT is the result of accumulating these things one after another. And the thing is that, and this is what is not intuitive to people, is that progress is an S-curve, right? You can add a bunch of small things, each of which looks, I remember reading the AlexNet paper and going yeah, this is cool. They've scaled it up with GPUs. Yeah, next, right? And you can see why, right? I didn't say oh my God. I was wow, these results are remarkably good. And, I wonder if they're for real. Same thing that the people in business are, right? I didn't say my God, this is going to change everything. But that's the thing is if you accumulate enough of these things, there comes a point at which you are ready for a phase shift. Now, how much of here's the important question. How much of a phase shift? So ChatGPT in some ways is an incremental improvement, but in some ways maybe it's not, right? Mm-hmm. Another question is, at what point in that S-curve are we now, right? And I think ChatGPT is a noticeable steepening of the curve compared to what we had a year or two ago. But this is AI, right? So there's even that steepening is very small compared to what's to come.
Yeah. Well, definitely, if you talk to people in the VC startup industry, they're definitely seeing it as a paradigm shift from there.
Yeah, and it may be for all I know.
Again, but they're still looking at ad platforms. So I want to, getting closer to the end here, maybe a bit of a double barrel question, but it's the one I've been dying to ask. So what areas of research, yours or others, are you most excited about for the future? And really the point I'm trying to get to is where does AI go from here?
Great question. So here are two possible views, right? One view, which is, these views are both common, but certainly the one that has the most visibility is like deep learning will get us there all the way, right? We just need to keep pounding on more improvements of deep learning and we'll get to AI. Yes, I think this is, for example, is the attitude of the pioneers like, Jeff Hinton and Yoshua Bengio and Jan LeCun is like, yeah, we understand that there are these so-called symbolic capabilities like reasoning and, problem solving and planning, but we're going to do all of that with neural networks. This is one possible approach. And, I can't prove that it's wrong. But I would say that, so here's another one. The counter is like, look at, that we touched on before, look at the history of machine learning. Every decade, kind of the dominant paradigm switches, and which is going to be the next, which one will come back, right? Like there's this joke that when NIPS started in the 80s, it was the Neural Information Processing Systems Conference, but then in the 90s it should have become BIPS for Vision Information Processing, and then in the 2000s KIPS for Kernel Information Processing Systems, right? And I remember having lunch with Yoshua Bengio at ICML in Montreal in 2009 and talking about this, and Yoshua said, so what do you think the next decade is going to be, right? That's the natural question. And I said to him, the next decade is going to be DIPS for Deep Information Processing Systems. And he started laughing.
As he should.
Laughing. If somebody had told us then that in a few years, deep learning is going to be on the front page of the New York Times, you go like, oh, buddy, what are you smoking, right? So, right?
Too good.
Really, what's happening is mind-boggling. But by that standard, maybe, there are people, and again, I've heard people in deep learning, leaders in deep learning say things are starting to slow down, the last big idea was transformers, and that was 5 years ago, so things are plateauing. This particular S-curve is coming to its end, and then we'll have to see what the next one is. And I think, it is a series of S-curves. I think there's so much to be explored in deep learning and so many people working on it that I think deep learning actually still has some longer to run, right? So it's not plateauing yet, is my guess, and this is just a guess. But at some point it will plateau. And then we are going to need to combine it with other things or come up with brand new things. The two biggest ones for me, or at least that I'm working on, are combining symbolic and neural AI. And again, I have an approach to that I've been working on called tensor logic, which I think solves this problem very well. We need to scale it up and all those things, but that I think is sort of like an obvious one to work on, to do in particular all those things that something like ChatGPT doesn't do, right? It's kind of like very smart in some ways, but ChatGPT doesn't know how to reason, right? A 3-year-old child can do things that it can't, and that people in symbolic AI know very well how to do. So I think this is one area. Another area which I wish there was a whole lot more people working on is just very different ideas, right? We should be letting 1,000 flowers bloom. Symmetry-based learning is one, but there's many others. Unfortunately, what we're seeing today is AI has never been bigger, but it's also, and that's good, right? But on the other hand, it's not healthy that everything is so concentrated on deep learning these days, right? There's been this giant sucking sound of AI is not just deep learning or even just machine learning, right? But now everybody's 90-something% of the people seem to just be doing deep learning, and not even just deep learning, but a particular type of deep learning. In fact, the International Conference on Learning Representations, which I often attend, which is the conference on deep learning, I often think that maybe what it should be called is the International Conference on Applications of Backprop. Because that's true. Even if you look at the whole scope of deep learning in terms of representation learning and things that people like, Jeff Hinton and others have worked on, it's what we're seeing now is a narrow slice of deep learning, which is a narrow slice of machine learning, which is a narrow slice of AI, which itself probably still only a narrow slice of all the things that we should be exploring. So I think we need to have a lot more people exploring a lot of things, and that's what we're not seeing enough of.
So last question, Pedro. Again, incredibly insightful answer there. So what advice would you give to young practitioners in machine learning and data science? Because I hear what you're saying, deep learning, we're not quite there yet. So you're not retiring yet, but what advice would you offer to folks out
That
there?
is a great question, and one that I get asked often. And usually my number one answer, which won't surprise people who've been watching the rest of this interview, is don't be a man with a hammer. If you're a man with a hammer, the world is just made up of nails, right? And the thing is that, again, this was one of my biggest motivations for writing the book, was this frustration that people have their paradigm, whether it's Bayesian learning or these days deep learning or whatever. And then what often happens is that you went to school or you learned from someone who was a member of one of these paradigms, and you think it's the only one there is or the only good one. And then you try to do everything, whether your ham is Bayesian learning or symbolic AI or deep learning or whatever, then you just approach everything with that hammer. And then you wind up, trying to pound screws into walls, right? Which is not good. Or if you're a company, I've seen this so many times, like you waste 2 or 3 years of your best people's time, gradually, heuristically making your way from the wrong thing that you started with to the one that you should have started with if you'd known a little bit more. So you don't just want to learn one thing, you want to have a view of the whole waterfront in machine learning and AI. And then what you do when you have a problem is you try to pick out from all that things that the few ones that look most promising, and then you try those, and then you iterate, right? And this is where really the big value of a machine learning person is not just that you know how to hack GPUs to do gradient descent or something. It's that you have a lot of this art and instinct of figuring out what is the right place to start, the right technique, how to modify it, as opposed to, like I have a hammer, right? I have, this neural network architecture, and that's what I'm going to try to use for. I mean, even today, right? Deep learning gets all the press, but for most applications, the best approaches are things like XGBoost or random forests or kernel machines or whatnot, right? So and often when I say this, people go like, oh no. And it's like, my number one advice to people from industry is like, deep learning is fine, but why don't you try nearest neighbor or logistic regression first? Because that often gets you 90% of the way. And then finally, you'll spend 10 years getting the last 2% with fancier techniques, right? So they're good. But trying to start with the hard part is actually kind of, a silly thing to do.
No, it's incredible. Like when we do polls ourselves or ask people, and I see it as well, what are the most common algorithms still used in the industry? It is random forest and whatnot. But Pedro, we're coming to well over an hour now, and so I got to say thank you for such a great conversation, such an illuminating perspective, and very astute observations. I would tell people to check out your Twitter handle, which we shared at the start of this conversation. Check it out on Twitter. Lots of great insights there, of course. Check out Pedro's research page. Lots of good sources on there. And of course, his machine learning course is online. It's still on Coursera, right?
No, it's not on Coursera because they at one point they switched to you have to pay and whatnot. And so, I just want my course to be free. So it's on YouTube. So it's the same
on YouTube.
thing.
Yeah, excellent. Yeah.
It's on YouTube. Yeah.
So yeah, on YouTube. So go check it out there. And Pedro, thank you once again. I hope to see you at the next, what is it, DIPS conference in the future.
Or who knows, maybe SIPS.
SIPS or DIPS or I think
yeah.
Yeah, so Pedro, thank you so much once again. And to our audience, thanks for listening in. I know it's a long conversation, but well worth the investment of your time. Pedro, thank you again. Really appreciate it.
Thanks for having me.
Bye now.
Bye.